Okay, so we're going to continue on with some more examples of doing optimization. So this is problem 43 in your book. What we have is a circular piece of wood, and we're going to cut it of a certain height and of a certain width to maximize the strength of the beam. So it says the strength S of a beam is directly proportional to the width and the square directly proportional to the square of the height. What are the dimensions of the strongest beam that can be cut from a round log of diameter 24 inches? And the equation that we're trying to maximize is strength equals some constant K times the height squared times W. So the first thing we do is we just define some variables. So we're going to define H as the height in inches, W is the width in inches, D is the diameter of the log in inches, S is the strength, and is there anything else? K. K is some proportionality constant, kind of like spring constant. And you say, well, don't we need to know what K is to solve the problem? Well, the answer turns out not to be no. So it doesn't really matter what the proportionality constant, the ratio of the height and width to give you maximum strength is what's important, not the proportionality constant. Okay, so that's step one. Identify all the variables. Secondly is write a primary equation for the quantity that is to be maximized or minimized. So in the problem statement it says we want to maximize strength. So here's the equation. Now K is just a constant, so we don't have to worry about that. But these are two variables. When we change the height, we'll change and that should be not diameter, that should be width. Sorry. So, if we change, because we're cutting it out of a fixed log, if we make the width smaller, we'll make the height larger. If we make the width larger, we'll make the height smaller. So these are tied together through, that's going to be our secondary equation, is the relationship between H and W. And you can see on the drawing that, what do I have here? What kind of triangle? Right triangle. So what theorem applies? Pythagorean theorem. Yeah. So W squared plus H squared equals D squared. And D is a constant because we're cutting it out of a fixed diameter log. So this is constant. So we should be able to solve for H in terms of W or W in terms of H. So the secondary equation, so this is my primary. Again, the primary is the thing we're trying to maximize or minimize. So the next one is we're going to have that D squared is equal to W squared plus H squared. And the one that makes the most sense to solve for is H squared, because we have H squared in the original equation. We don't have W. We just have W by itself. So actually, why don't you do this so you can do the rest of it. So what I want you solve for H squared from this equation, substitute into here, take the derivative, set the derivative equal to 0, find the values of, in this case, H that maximize the strength. And ultimately you would want to, yes, do you want to get your test? Yeah. Yep, I know, I did. So there you go. The physics lab's open, so you can just go in there and finish it off. Okay, so go ahead. So solve for h squared, plug into this equation. Just like before, you want to multiply it out and then take the derivative. Instead of using the product rule, set the derivative equal to 0, find the values of h, which give you maximized strength. We could take the second derivative and show that it is actually a maximum instead of a minimum. So I'm going to So this is the simplified form. Reduce the primary equation to one having a single independent variable. So the independent variable in this case is w. K is just a constant, so you just treat it as a constant, even though it's not a number. And then take the derivative of this with respect to w. And then set it equal to 0. And that's where the k disappears, because you can divide by k. Have you guys finished, or are you looking? You're done. Okay, good. Oops. So once you solve for w, then you can go back. You could solve that for h. So there you go. So you get the width is 13.8 inches and the height is 19.6 inches. And this kind of relationship where the strength is larger or more influenced by the height than the width, there is, you may have heard of I-beams. They're used to make for construction purposes, so they look like this. So if you're building a skyscraper or any kind of big building, you'll have a beam that looks like that. And what they're doing with this kind of arrangement is they're basically in a building. So here's the side view. So you've got the top beam part and the bottom beam part. So these parts are thicker than the inside. And the further you put away, the most you put away as much metal as possible away from the center of the I-beam. Because what we're doing here is you're loading the beam. So you've got some kind of support on either side, and you load the beam and the beam bends. So, you know, like this paper, if I hold it, it sags. Okay, that's because this is so thin, but it does bend. So normal beam, it would look like it's flat, and then you load it and it's going to push it down like that. And it turns out to maximize or minimize the amount that the beam bends in the middle. An I-beam type construction gives you the maximum strength or maximum resistance to bending for the amount of material that you use, because you're trying to minimize cost in terms of material, but also in the weight of the building. So if I go to Google here, let's see what it says about I-beams. So there you go. There's an I-beam, also known as H-beams. I guess that's true if you go this way. They're H-beams, but let's see. Designed for bending. So it says what does S stand for here? You would assume it's strength, but I'm not making that assumption. Stiffness, probably. It's probably stiffness. And if you go down here and look, it's a function of this quantity, which we'll learn about in physics in a couple of weeks, called moment of inertia. And the moment of inertia is equal to the width times the height squared. That looks kind of familiar, doesn't it? So that's where that's where that equation came from. And so because the strength is dependent more on the height than the width, it ends up that you end up with a beam that's taller than wider to maximize the strength. You can even make it stronger if it was just made out of, for a tree, probably if you're talking about making the strongest beam out of a block of wood, it's probably still a rectangle. But if you were making it out of the minimum amount of material, then you would use an I-beam. But the key thing here is the I part can't be too thin, because then it'll buckle, and so you can't put everything. Can't have like just a sliver in the middle. That's not going to work. But you just need enough here to provide enough stiffness so it doesn't twist and things like that. Okay, so the feasible domain, as I said, was from 0 to 24, and when we took the square root here, we actually would have had plus or minus 13.8. and plus or minus 19.6. So we would not include the negative solutions as answers. We can't have negative widths. So that's how the fourth step comes into play. And actually we've done the fifth step. And again, if you look at the second derivative, so let's, they didn't ask us to do this, but where did my page go? There we go, that's what I want to. So if we take the second derivative, so we take d squared s dw squared. So we take this equation, you'll end up with negative 6k times w. This one goes to 0 because k is a constant, so the whole thing's a constant. And then you take the derivative here, and you got the exponent, which is 2. 2 times 3 is 6. So we get 6k. The negative stays negative. So what we would have is, for w greater than 0, the second derivative is going to be negative because of the negative sign. So that means concave down, which means unhappy face, which means it's a maximum. Okay. So it says, yeah, okay. So moving on here. So let's look at the next problem on the handout. next one's kind of difficult. It's not simple, so I have a little story. I think it's true. Let me search on the internet, see if I can find the story. Dog swims in direction to minimize time. Let's see if there's anything that comes up with that. Do dogs know calculus? Okay. Yeah, they were corgis. I thought they were corgis. Most calculus students are familiar with the calculus problem finding the optimal path from A to B. Optimal may mean, for example, minimizing the time of travel, and typically the available paths must traverse two different mediums involving different rates of speed. That's our problem. This problem comes to mind whenever I take my Welsh Corgi Elvis out for an outing to Lake Michigan to play fetch with his favorite tennis ball. Standing on the water's edge at A, I throw the ball into the water at B. By the look in Elvis's eyes and his elevated excitement level, it seems clear that his objective is to retrieve it as quickly as possible rather than, say, to minimize his expenditure of energy. Thus, I assume that he unconsciously attempts to find the path that minimizes the retrieval time. So what he does is he runs down the shore and then he jumps into the water. And he could run all the way down to the shore to be even with the ball and then swim out, but he never does. He always just goes to some point, intermediate point, and then jumps in and swims diagonally. I don't know if this guy's really true, but this is actual true story. It's like preachers. Sometimes you think they make up stuff just because it makes a good point, right? When it defies the laws of physics, then I start to question. But it's still good. It's a still good story, right? So anyway, this is this guy from Indiana. Let's check his story out here. Which lake is he going on? Lake Erie? I didn't say. Lake Michigan. Okay, that could be true. So far his story has stood up. Anyway, there's all these things. Does your dog know calculus? And whether it's a true story or not, I don't know. I assumed it was true. So let's draw a picture of this thing. In this case, it's not a dog. What we have is a boat out here. That's a funny looking boat. And we have the shore. And then we have some objective point here, some place he wants to get to. So that's point Q. Well, I don't know what Q stands for. Maybe it doesn't say what Q stands for. If it's a guy, that's a cute girl. What's the quickest way I can get to a... Okay, so what you do is you can go part of the way on the ocean, the water, and then you go the rest of the way diagonally on land. And each one has a different speed. So the boat, a man in a boat, is 2 miles from the nearest point to the shore. So this distance is 2 miles. I'm just going to put 2. We'll just do it all in miles. He is going to a point Q located 3 miles down the coast. So if I measure this distance here, that's 3 miles. And 1 mile inland. Okay, so this distance here is 1 mile. Now he can row at 2 miles per hour. So we'll use the rate. I'll leave the units off right now. So during this part, I'll put it in here. 2 miles per hour he can row, and he can walk at 4 miles per hour. And you might think, well, the fastest way for this guy to get from there to there would be to take the boat this far and then walk that, or run or walk. I guess walk. He's walking fast. So what we're trying to do is minimize the amount of time it takes to get from here to like the Corgi, except we're not starting on the the shoreline. We're starting out from the shore and we're going into the shore. So what you can see is we have a couple of triangles, and we know this side of the triangle, and we know this side of this triangle, and we know that the my dimension mark is not really right in the right place here, so let's move that. So this one is right there. Okay, so it's 3 total miles. So we have to introduce a variable of some kind. Now you may be tempted to say, well, the distance here is x, and the distance from here to here is x, and the distance from there's y. And that would be sort of okay. But there's another way of doing this. If this is x, this distance is x, what would be the distance here? So this is 3. Total distance is 3. This is x, so this is 3 minus x. So we get it in terms of one variable. Okay, now what they're asking is for time, how long it takes. So from physics, it says delta x is equal to the velocity times the time, or the time is equal to the displacement divided by the velocity. So that in case of the part on the ocean, it's going to be the distance I travel here divided by the speed, which is 2. So let's use capital T for total time. So capital T equals total time. And so the total time is going to be the time for, we'll call this this part A and this part B. So it's going to be the time to go from here to here, which is in the water, and it's plus the time it takes for you to go on land. And the time is going to be equal to the displacement for part A divided by the speed, which is 2, plus the displacement for part B, which is that divided by 4. So there's our individual times as the total time. The total time is the thing we're trying to minimize in this case. And these distances we can figure out in terms of x. So what is the value, what is the length of this side from Pythagorean theorem? So let's call this L sub A, or delta x sub A, either way. So L sub A is going to be equal to the square root of 2 squared plus x squared. And the length for the B part is going to be equal to the square root of 3 minus x squared plus 1 squared. So now you can stick those into your total time, the thing we're trying to maximize. So we'll have the square root of 4, 2 squared is 4, plus x squared, divided by 2, plus the square root of 3 minus x squared plus 1, all divided by 4. So we didn't, our secondary equation was really when we made this relationship. If we had used x and y, we would have had a primary equation that had x, 2 variables. And then we could have related x and y in this way, but I just went ahead and did it. So now we have to take the derivative of that thing and find the values of 0, find the values where the derivative equals 0. Now it's kind of like the other ones that we've used, you know, the distance formulas. I mean, you can do, you could use the chain rule to take the derivatives. or you could see if there's any way you could think about how you might be able to rewrite this in the simpler form. In this case, I don't think there is that much of a simpler form. So before we take any derivatives though, let's take the second term and just multiply it out. So if we multiply this out, we'll get 9. Well, 9 plus 1. 3 squared plus 1 is 9 plus 1, which is 10. So I'm just going to put 10 in there. So you get 10. And then you'll have minus 6x plus x squared, all divided by 4. I guess one thing you could do is you could just multiply everything by 4. 4t is equal to the square root, 2 times the square root of 4 plus x squared plus the square root of 10 minus 6x plus x squared. The advantage there is you don't have to deal with fractions at all. So if I maximize 4t, I'm going to maximize t. It's not going to. So now go ahead and take the derivative. See if you can remember how to take the derivative. We'll call this t star, which is 4t. So we'll take the derivative of t star with respect to x. And what you'll need to do is use the you'll need to convert these into, the half power. And then use the chain rule and the power rule to do that. So I'm going to let you think about that. Once you do that, you can set it equal to 0. So the way to think of this is, I've got my constant 2. The power rule says that I take the exponent and I multiply by what I started with and reduce the exponent by 1. So that becomes negative 1/2. But the chain rule says that I can't just do that. I have to take the derivative of what's inside the parenthesis. So this is that, the exponent, keep this the same, reduce the exponent by 1, and then multiply by the derivative of what's inside. So if you do the same thing for the second part, you'll have, we don't have the 2, so we don't include that. We have 1/2, which is the original exponent. We take the argument of the thing we're taking the derivative of, and we raise that to the negative 1/2 powers because we reduce this exponent by 1, and then we multiply by the derivative of this, which is going to be negative 6 plus 2x. So let's just take a little side here. So let's say if I had 4 times the square root of x cubed plus 3x minus 7, and let's call that f of x. So f prime of x is what? Okay, so before you'd rewrite this as to the 1/2 power. And go ahead and do that, just to make sure you understand what I've done over here, okay? Now ultimately, what I'll do here is these cancel out. This goes to the denominator. So I get 2x divided by 4 plus x squared to the 1/2 power, positive 1/2 power, because I've moved it to the denominator. And over here, I'll have 2x minus 6, I changed the order there, divided by 2 times 10 minus 6x plus x squared to the 1/2 power, and then ultimately I can change that to the square root of 4 plus x squared, and over here I can do the same thing. So I have 2 times the square root of 10 minus 6x plus x squared. So do this one as well. See what you get. takes a lot of space to do it the long way, and just doing it this way means you are maturing as a calculus student. You're not having to do the simpler ways anymore. So I'm going to come around and see how people are doing on that. So that's the answer you should have. So you get 4 times a half, the exponent, reduce the exponent by 1, keep the argument the same, multiply by the derivative of what's inside the parentheses. And then this goes to the denominator and becomes a square root. When that becomes a positive 1/2, then it becomes a square root. Okay, so back to our problem here. So you're going to set that equal to 0. So we got to figure out what values of x cause that to be maximized. So there's a couple of ways of doing it. One is you could find a common denominator, which would be a lot of work. So here's a little trick. So if I were to move this term to the other side, so nothing's changed. I mean, the equation's the same. And what you could do is if you square everything, so if I square this and I square that, it's still equal because I'm doing the same thing to both sides of the equation. So what happens is when you square this, you'll get 4x squared. The negative will become positive. The denominator, you get 4 plus x squared. The numerator here, you'll get 2x minus 6 squared, so we're going to have to multiply that out. And the denominator becomes 4 times 10 minus 6x plus x squared. And then what you would do is you would, I'm going to go ahead and square that thing out so that you'll get 4x squared minus 24x plus 36. So 2x times 2x is 4x squared. 2x times negative 6x is negative 12, but it happens twice, so you get negative 24. And this negative 6 squared. And then we'd have, I'm going to go ahead and multiply the denominator out. 40 times negative 24x plus 4x squared. Then you can cross multiply. So you'll have 4x squared times 40 minus 24x plus 4x squared is equal to 4 plus x squared times 4x squared minus 24x plus 36. And then you're going to multiply that out. I'm going to let you do, well, actually, I'm going to give, this is a homework assignment. So I'm going to tell you how to do it. So what you do is you multiply all this stuff out, combine like terms, and you'll end up with a fourth order polynomial. So it'll be something x to the fourth plus something x to the third plus something x cubed is equal to 0. So go ahead and do that for Monday. And then what we'll do is once you get the answer, we'll talk about how we find the roots of a fourth order polynomial. So it's not a trivial situation. But I want you to do the algebra. It'll take about 10 minutes, and I'd rather you do that rather than spending 10 minutes of class time. Okay, so the math gets pretty complicated here. The key thing to remember, let's go back and not get lost in the algebra. So the optimization situation is we defined variables, which it turned out we only had to define one variable ultimately, which was x, the distance from here along the beach to where he touches the beach. The domain is going to be between 0 and 3. X cannot be greater than 3. We were able to come up with an equation for the total time required to traverse from here to here based on traveling some variable distance x this way, but doing it diagonally. So we ended up using the Pythagorean theorem. But basically we have a single equation to maximize in terms of a single variable. We're going to take the derivative, set the derivative equal to 0, find the values of x where the derivative equals 0. Those are our solutions. In this case, we may have as many as 4 solutions because we end up with a fourth order polynomial, but only one of them will be between 0 and 3. That also helps us. We don't care what the other roots are. We only care what one root is. We care about the one root that's between 0 and 3. So that's something that helps us as well. So we'll come back to that. Okay, what else we got going on here? Done that one. I'm going to go ahead and give you the homework. Oh, there we go. Homework assignment. So those are due next Friday. Yeah, to be honest, when I looked at that problem the first time, I didn't know what to do either. So it may seem, I don't want to give you the impression that, oh yeah, that's easy stuff. It's not easy. Some of the stuff we have fairly simple algebra and fairly simple derivatives, but I like to have at least a couple of problems that go into a little bit more detail relative to the difficulty of doing the algebra. The calculus is the same. It's kind of like in pre-calc. Let me ask you guys this question. So when you had pre-calculus last year with Mr. Appel, he spent how many weeks reviewing? Maybe 3 weeks reviewing previous stuff, appendix? What's that? It wasn't that long? Oh, it wasn't 3 weeks? Oh, was it really? Okay, I thought he took longer than that. Okay, I usually don't do any kind of review. What I do is kind of like in here, is when we get to something that you might need a review on, I do it as part of the class instead of putting all the review at the beginning, and then by the time you get to it again, you've probably forgotten what the review was. So anyway, that's my approach. Mr. Watkins and Mr. Appel, they do the review first. And I know you guys, I know the governor's school students have had pre-calculus last year, so it's not like it's been 5 years. So that's another advantage of that situation. What I'm going to do is we're going to talk a few minutes about what we're doing next in section 8, but we'll come back and do a few more optimization problems. But I don't know about you, but I'm ready to think about something different for a minute. Okay, so section 8 is called Newton's method for finding roots of functions. So for example, the problem we just did, we've got a fourth order polynomial. It may be a rational root. That'd be nice. I think actually it is. Turns out to be either one, two. It's either one or two, but it's just a coincidence that works out that way. But if you picked any other speeds besides 2 and 4, I don't think it would come out to be a nice rational root. And if you go back to, remember the in section 6, we were working on that problem to start with, and I said we'd come back and talk about it later. So this, when we were doing the curve sketch for this function, x cubed plus 12x squared minus 5x plus 20, and we tried using synthetic division to find a root, and we said, we ultimately said it was somewhere between negative 10 and negative 20. Because at negative 10, the value, x value was 270, and at negative 20, it was negative 3080. So we know the root's somewhere between those two. So the question is, how do we get to the answer quicker than just kind of guessing and trying different numbers, trial and error? That's what we're doing in this section. And it's called Newton's method for finding roots of functions. So can we use calculus to help us find the roots or zeros of a function? The answer is yes. Okay. So this is a sketch that goes kind of with, and it's kind of like, I think your calculator, don't you, when you're looking for roots, you have to put in some kind of a initial guess of some kind. Is that true or not? I don't remember. I don't know the calculator very well. I vaguely remember something like that. You might have to put an initial assumption. So what I have here is a function. This is the black curve. And I've got an x-intercept right here, which I don't know what it is. I know I have a reasonably good idea of where it is, just like in the problem I just referenced. So I'm going to pick some value of x that I think is close to it. So this is my initial guess for the root, and it's not correct. It's wrong. So if I were to put this initial guess into my original function, I would get something other than 0. I would get this value of the function. But what I can do is I can take the derivative of this function, because it's an equation, and I can find the value of the slope of the tangent line at this point. So I have this point, and I have this slope, so I should be able to define this line. And with this line, I can then find where this line, this tangent line, intersects the x-axis. And that's going to give me an approximation for the actual 0, rather than just guessing. I'm kind of extrapolating based on the known slope at this point and the known value of the function. Then what I do is I take this as my next guess, and so I find the value of the function at this value of x, find the slope, and then, so let's do that. So let's say that my next guess is this one. Well, my next guess is not a guess, because I've estimated where the function intersects. And if I take the slope of the tangent line there, my next guess will be here. And then I take that guess and do the same thing, and you just keep iterating. And you can see after maybe about 3 iterations, you can get very close to the actual root, because as you zoom in, as you get closer and closer to the actual point, the curve becomes more linear. So let's just demonstrate that point. We've done that before. But if I plot a function like y equals x squared, you know, I can see the curvature at this level of magnification. But if I zoom in on some area, then the curvature becomes less, and then I zoom in on a smaller area and it's starting to look like a line. So that's why it doesn't take that many iterations to go from missing it the first time to getting the final solution in a very short period of time. So that's what we're going to do on Monday. I don't cover this. This is not on the test. So everything that is on the test we have already covered. It's going to cover section 3.1 through 3.7. 3.6 will be a take-home part of the test, but so it's the actual in-class test is sections 1 through 5 and section 7. Okay, so we'll see you on Monday, or we'll see you in about 15 minutes, depending upon who you are.